Yes, good afternoon, everyone. Welcome to the another session on Engineering Mathematics 4 here. And today we'll discuss the two application problems based on the topic partial differential equation here. Partial differential equation. Yes, we are going to see two problems here. Draining of liquid down the side of a vessel. This involves a first order equation, first order linear equation, like Lagrange's linear equation. And another one is a telegraphic equation, transmission line equation. Transmission line equation, that is a telegraphic equation. And the two things we are going to see that two application problems we are going to discuss now here today. The first one, the liquid down the side of a vessel here. Liquid drains down the side of vessel. Very simple problem only here. That contains Lagrange's linear equation. Lagrange's linear equation idea. You see that here, a liquid down the side of a vessel here. Liquid down the side of a vessel here, and then for which we have its motion is governed by the equation. A thin layer of a liquid, drains down the side of a vessel here. Drains down the side of vessel, whose motion is governed by the equation. Motion is governed by the equation. It drains down the side of a vessel here. Therefore, at what distance is drains down here, that will be the distance is x. The time duration, and the different time duration, it reaches different distance here. That is also very important here. Therefore, whose motion is governed by the equation dou h by dou t plus a h square dou h by dou x equal to 0 here. This is already a derived equation. But you have to remember this equation only. You have to remember this equation here. Whose motion is governed by the equation dou h by motion is h, and the h is depends on both the distance it falls and also the time duration it reaches. Therefore, it depends on h and t. Therefore, dou h by dou t plus a h square dou h by dou x is equal to 0. A h square dou h by dou x equal to 0. For your work is that you have to identify what is h, the distance, the motion we are going to discuss here. The motion is given by this equations h of x comma t, where h of x comma t is the thickness of the layer, and a is a constant that depends on x is the distance is going to cover here, and then where h of x comma t is the thickness of the layer, and a is a constant. That depends on the viscosity, density, and the gravity. Viscosity, density, and the gravity. Find the solution for h of x comma t, given the initial condition h of x comma 0, that is equal to alpha times the distance is going to cover square root of x, where alpha is a constant. For the one problem we are going to discuss here, this motion is governed by the equation, where h of x comma t is the thickness of the layer, and a is a constant. And find the solution for h of x comma t. They are asking that find the solution for h of x comma t given the initial condition. This is h is here. That will be the thickness of the layer that we are going to consider here. Thickness of the layer. This is h here. H of x comma t is the thickness of the layer, and a is a constant here. And you are going to interested to find the solution of h of x comma t, and the initial condition is given as h of x comma 0 is equal to alpha square root of x. H of x comma 0 equal to alpha square root of x. For the equation we are going to solve, that is dou h by dou t plus a h square dou h by dou x equal to 0. Dou h by dou t equation we are going to consider as a dou h by dou t Equation is dou h by dou t plus a h square dou h by dou x is equal to 0. A h square dou x by dou h by dou x is equal to 0 again. Therefore, from this we are going to identify what is h of x comma t. H of x comma t. Here, the given equation is of the form pp plus qq is equal to r here. Pp qq equal to r, where small p is dou h by, like dou z by dou x, here dou h by dou x. Small q is equal to dou h by dou t, like dou z by dou y, here dou h by dou t. Capital P is a h square, capital P is a h square, and capital Q is equal to 1, and R equal to 0. R equal to 0. These are the form of PQ equal to R, the form of Lagrange's linear equation. Lagrange's linear equation. For auxiliary equation, our subsidiary equation is dx by p instead of dx, here dx only. Instead of dy, here dt you have to use here. dt by q, and instead of z here h here, dh by r here, instead of z, so on. Since here h of x comma t, h of x comma t instead of z of x comma y, instead of z of x comma y, we are going to consider h of x comma t, h of x comma t. For dx by p a h square, dt by q is equal to 1, and dh by r equal to 0, r equal to 0. Therefore, when you club these two here, first two you can get it as last two here you can get h is equal to constant, you can get here, by second and third proportion, second and third proportion, what you can get here, dh is equal to 0, integrating implies you can get h is equal to c, a constant, h is equal to c, a constant. This is one thing. By first and second proportion, what you can get here, dx is equal to ah square dt, ah square dt, but h you can write it as c, c, or ac square constant here, ac square dt, dx is equal, or you can get it as x is equal to ac square t, x is equal to ac square t. That will be the relation you can get, ac square d t, you can get that. X is equal to ac square t. That relations you can get here. From this you have to identify the h value, ac square t plus k, you can add additional k here, where c and k are arbitrary constant. Therefore, we are interested to find the solution of the equation is h is equal to c, h is equal to c, or you can write it as x is equal to the two solutions you can write here, two solutions here. H is equal to c, k is equal to two arbitrary constants, because Lagrange's linear equation means two things you can identify here. X is equal to ac h square, ac h square, that type of idea you can get. Therefore, you can get x is equal to ac square plus t, c square plus a, or so on here, or some constant you can write here, some constant you can write. Here h is equal to constant here, h is equal to z equal to constant, that is one thing, and then here x is equal to ac square t plus k here, but already c is h here, We can write it as x is equal to a z square, a z square, sorry, a h square, not z, h, a h square t, a h square t plus k, that is x is equal to x minus a h square t equal to k. X minus a h square t is equal to k. And here is also one solution. This is one solution. Suppose you say this one as a u, say u say, and this one as a v say. Therefore, general solution is phi of u comma v is equal to 0. Here h is equal to c here, first one. Another one is x minus a h square t. X minus a h square t is equal to 0. Or otherwise you can write it as a function, h is equal to function of x minus a h square t, a h square t. Or otherwise you can write leave these two are solutions. These two are solutions. H is equal to c and x minus a h square t, x minus a h square t is equal to k, and that will constitute a solution. These two constitute a solution. So like a general Lagrange's linear equation idea, you can write the general solution as a this one. We are interested to find h in terms of x comma t, h in terms of x comma t. Yes, from this you can write h is equal to x comma t from h is a x comma t from this function, general function. This will be the solution of the given problem.
Sir,
Uh,
if we forgot to write H as C, C as H, then it will be wrong, sir.
if you
The
what
last
about
resolution, sir.
this one now? What about
In
your
general
question?
solutions are 5 of
Pi of
here, sir. If
uh,
we forgot to write C as H, sir,
CSH. Okay.
directly
Now
writing phi of H comma x minus AC.
AC square t, yeah, AC square t. AC square t, no problem. But already it is given that h is equal to c na, in the initial condition. In the previous solution, you obtained h is equal to c. So even though if you write AC square t, AC square t, you can say that already C relation you know that. C relation you know that. Or both are same. Otherwise you can write here, no problem. It's not a mistake here. But you have to mention that this condition. This condition is mentioned. You have to mention. Okay.
Okay.
This is the solution of the liquid draining down using Lagrange's linear equation idea. Lagrange's linear equation idea. Okay. Then next one, we are going to see that telegraphic equation, transmission line equation, that type of problem. That type of problem.
Sir, here they give an initial condition.
Oh, initial
Previous.
condition. H of x comma 0 equal to alpha root x. Suppose if you write like this here, a h square t is equal to k, a h square t is equal to k minus x, k minus x. A h square t is equal to k or x minus k minus x, x minus k, x minus constant here, and the condition is given as h of x comma 0 equal to alpha root x, h of x comma 0 t equal to 0, Uh, here you see that here this is hx comma t, hx comma t, hx comma t is equal to 0, c. hx comma 0 is also not unaltered here, Therefore, you can see, you can take the same value here. You can take the same value here, same value. Okay. Right. Because this only gives that h very clearly. Here you are replacing c as a h. It is not direct h here, direct h. From this relation you are getting. Therefore, here only you are getting h is equal to c. For h is equal to c means h of x comma t. Okay, h of x comma t is equal to c. But h of x comma t means h of x comma 0. From this, if you put that here, it is also unaltered here. Okay, unaltered here. Base you can get it as h of x comma 0. What is the thing it is given? Alpha root x, alpha root x. Alpha root x is equal to c. Alpha root x is equal to c. Therefore, we are getting c value as a alpha root x. C value is a alpha root x. For h is equal to c, but that c can be written as alpha root x. That c can be written as alpha root x. Therefore, here you can write here. Okay, here you can write c as a alpha root x. That value, that initial condition useful for finding that constant c, constant c. And that one I can write here. Therefore, also given that you can write that initial condition. After this, before finding this one, you can write like this. You can apply initial condition. You can apply initial condition before applying first and the second proportion idea. First and second proportion. You can write clearly in terms of C. H is equal to C here. Also given that h of x comma 0 is equal to alpha root x. Alpha root x. Therefore, h is equal to C implies h of x comma t is equal to C. H of x comma t is equal to 0. Implies h of x comma 0 is also C. Implies alpha root x is equal to C. Therefore, C is equal to alpha root x. Therefore, implies h of x comma t, h of x comma t can be written as C, that is equal to alpha root x, alpha root x here. Implies you can write as h is equal to alpha root x, h is equal to alpha root x. This is from one condition, one condition. H is equal to alpha root x is equal to u say. Again by first and second proportion. Therefore, instead of C, you can write alpha root x. First and second proportion. You can write dx by a h square equal to dt by 1. Equal to dt by 1. Now you can apply h is equal to alpha root x here. A alpha square h square root x means x equal to dt by 1, since h is equal to alpha root x. I forgot to apply the initial condition. Now you can write like this here. Dx is equal to dx by x is equal to a alpha square dt. A alpha square dt. A alpha square dt. Integrating implies log x. Log x is equal to a alpha square t plus c. Some constant k. Constant k. Therefore, you can write it as x is equal to e power alpha a square t, e power alpha a square t plus a constant capital A, capital A, because e power k A is equal to e power k. A equal to e power an arbitrary constant, an arbitrary constant. Or it may be x by e power alpha a square t equal to e. X by equal to v, say, by Lagrange's linear equation idea, you can write like this. That is nothing but x e power minus a alpha a square t, negative exponential, that is equal to v. For general solution is pi of u comma v is equal to 0. H is equal to alpha root x, alpha root x, that is equal to h minus alpha root x. H minus, you can write like this here. H minus alpha root x, or h is equal to so on. If you write means h minus alpha root x, you have to write that u h minus alpha root x comma x e power minus alpha a square t equal to 0. Pi of u comma v is equal to 0. From this you can write h is purely in terms of x comma t. H is purely in terms of x comma t. Here x and here xt, xt here. So you can write h as a x comma t form. H as x comma. So this will constitute a solution. This will constitute a solution. Here you can write h minus alpha root x. H minus alpha root x is equal to u, say. Here h is equal to alpha root x, or h minus alpha root x equal to u. Because of initial condition, we can apply initial condition h x comma 0 is equal to alpha root x. X comma 0 equal to alpha root x. Therefore, h is equal to c inverse h x comma t equal to c. Here we replace t is equal to 0. T equal to 0. That is nothing but alpha root x. Alpha root x equal to c. Alpha root x equal to c. Therefore, we can get it as alpha root x. So the solution will be like this. We have applied initial condition also. Sorry for not applying the initial condition. Okay. Yes, this is the idea. I think all of you understand here. These are the form, the given equation, or the form of Lagrange's linear equation. Lagrange's linear equation, Pp q equal to r. And this equation represents draining down of a liquid from a vessel. Dou h by dou t plus a h square dou h by dou x. H square dou h by dou x. And here h represent density. H represent thickness, not density here, thickness of the layer. H thickness of the layer. This is the a liquid. A liquid down here. For how the density, this is a vessel distance here. Because the lower part you can get a thickness, thickness of that liquid layer. You can get somewhat high here, or that will be the thing you can get that. Or here you are finding that solution of hx comma t. Hx comma t is the thickness of the layer, and a is a constant. That thickness of the layer is depends on the viscosity of the liquid. Viscosity, similar density, and the gravity. Gravity, how fast it moves depends on the gravity. Depends upon that the thickness of the liquid layer. Thickness of the liquid layer varies here. So it depends on viscosity, density, and gravity constant. And here from this equation, we are finding the solution of hx comma t. Hx comma t with some initial condition. Initial condition alpha root x, or alpha is a constant here. Alpha is a constant. So we are solving this equation for getting how far the thickness of the liquid, how far the thickness of the liquid when it's fall down from the vessel here. Drains from the vessel layer, side of the vessel, drains down the side of. Then what will be your thickness? How long, and what will be the thickness of the liquid here, liquid that you are going to identify here. That is the idea. For that, we are solving the equation dou x by dou h t a h square dou h by dou x equals 0 with the initial condition. Initial condition. This is the equation dou h by dou t. Or here it is of the form pp q equal to r here. P is equal to dou h by dou x, q is equal to h by dou t, and everything. We are solving the equation. With the help of this, immediately you can find h is equal to c, but h is nothing but h x comma t. Or applying the initial condition. From that you identify that C also alpha root x idea again. Then now you are getting h is equal to alpha root x. H is equal to alpha root x. So replacing h is equal to alpha root x here. You can club in the first and second proportion. You separate x and the t here. You can get correspondingly some relations. This will be your solution. H in terms of x comma t. Thickness of the layer of the liquid. Now move on to another set of equation. Telephone equation, transmission line equations here. The transmission line equations here they are using the notation as a rho, but instead of rho you can also use V. V means the potential difference, because here rho you are going to consider as a potential at a point of the cable here. For potential you can also use the V. Current I is equal to current here. LC inductance and capacitance, everything. L inductance, C capacitance, R resistance, leakage of the ground per unit length of the cable. Leakage of the ground per unit length of the cable, that is G. What is resistance? So we have remember these two equations here. These equations are already derived equations here, but it is a second order PD. Second order PD, dou square rho or dou square V. You can use here, dou x square equal to LC dou square rho by dou t square, or dou square V by dou t square. Any manner can write here into plus RC plus LG by LG. G represent leakage to the ground per unit length of the cable. Dou rho by dou t RG. Here your aim is that you are seeing that partial derivatives here. Standard order partial derivative rho r v in terms of x comma t. Rho r v in terms of x comma t. Rho in terms of t x comma t. Similarly here current I, that equation also given here. Together form these two equations together form a telephone equations. They are known as telephone equations here. Dou square I by dou x square equal to LC dou I by dou t square plus RC plus LG dou I by dou t plus RG I here. This is RG rho or RG V. Suppose if R equal to 0, G is equal to 0 here. R 0, G is equal to 0 here. Resistance and leakage to the ground, both are 0 here. And then correspondingly, these values get changes here. Dou square rho by dou x square here. And LC dou square rho by dou t square. R0, G 0. Here is also R0, G 0. You can get on first two parts only. First two parts. Similarly, here is also first two parts only here. Dou square I by dou x square. LC in dou square I by dou t square. Now these equations are called radio equations. These equations are called radio equations. Particularly R0 and G0. The notions are There's a problem is that find the solution of differential equation that governing the propagation of current and potential along on the transmission r equal to 0, g is equal to 0. Okay. If r equal to 0, g equal to 0 means these equations only you can consider. Okay. Dou square rho by dou x square or dou square v by dou x square, LC is equal to so on. Okay. Therefore, these two equations only you have to consider. Initial condition that rho x comma 0 is equal to f of x and dou rho by dou t, dou rho by dou t of x comma 0 is equal to 0. Okay. Two initial conditions are given here. At time t is equal to 0, the potential along the cable, potential at a point of the cable, potential at the point of the cable, that will be given as in some function, some functional form here, functional form of x here, and then at time t0, a gradient rate of change of that potential difference at time t is equal to 0 here. Time t is equal to 0. That's also given here dou rho by dou t at x comma 0 equal to 0. That is given as a 0. That value equal to 0. Because r g0 g0, you can use the radial equations here. Dou square rho by dou t square equal to a square square rho by dou x square. A square to 1 by LC. Square given that dou square rho dou t square equal to so on a equal to 1 by LC. They are writing the equation in the reverse manner. Reverse manner. The second problem, since r is equal to 0 and c is equal g is equal to 0, we have the radio equations. What are the first you consider this one. First find the rho, and then you can use the relationship between that v and I here. Dou square rho by dou x square. Sorry for the interruption. It will be internet error. Yes, it is a second order ODE. Therefore, you have to solve the second order ODE. You have to solve the second order ODE here. Therefore, with the help of that, you can get it as two roots here. Two roots here. I think no need to write here a square as a 1 by LC. If you write a square as a LC, that is the best choice. A square as a LC, that is the best choice you can use here. Because we are writing that function of f of x plus at form here. One two roots are a and a here. So I think no need of this one here. No need of this idea. A square equal to 1 by they have given some wrong notes here. Okay, instead of that you can write a square so on here. You keep as it is here. No need to change this one. You keep as it is. You write like this here: dou square rho by dou x square. That is equal to a square into dou square rho by dou t square. Where a square equal to LC. A square equal to LC. Now it is like a d dash square d square. It will be like a second order equation. It will be like a second order equation. Second order PD d square minus a square d dash square. A square d dash square of rho like az, that is equal to 0, where d is equal to dou by d square means dou square by dou x square. D dash square means dou square by dou t square. Dou square by dou t. So this will be the equation. Therefore, to get the solution of 1, we need an auxiliary equation of 1. To get the solution of 1, we need an auxiliary equation of 1. M square minus a square equal to 0. We replace d by m. Replace d by m and d dash by 1. Replace d by m, d dash by 1. Therefore, m is equal to plus or minus a. M square equal to a square, m is equal to plus or minus a. Because of plus or minus a, you can write it as solution is rho of x comma t, that is equal to function of y plus pi 1 of y plus ax plus pi 2 of y minus ax. That is rho of x comma t. Pi 1 of y plus ax plus pi 2 of y minus ax. Pi 2 of y minus ax. That is rho of x comma t. Rho of x comma t. That will be the solution. Just you write it like a what? Second order ODE. Second order ODE of homogeneous type. Second order ODE of homogeneous type. With the help of that, we can write this solution. Further, you can write R. A as a LC form here. Rho of x comma t. A is equal to a square equal to LC. Therefore, a is equal to root LC. X into square root of LC plus pi 2 of y minus x into square root of LC. Since a square equal to square root of LC. Right. In that manner, we can write that. This is solution here. Further, some initial conditions are given here. The initial conditions are given. Also given rho of x comma 0. Okay, rho of x comma 0, that value is given. Rho of x comma 0 equal to f of x. Rho of x comma 0 equal to f of x. And similarly, dou rho by dou t x comma 0 equal to 0. Dou rho by dou t x comma 0 equal to 0. Rho x comma 0 equal to 0. Comma substitute in 1. Substitute in 1. Rho x comma 0 equal to 0. Here 0. T is equal to 0. Sorry. We can write x plus at form. X plus 80. Instead of y plus ax, you have to use x plus at. Because x comma t, not y comma x. X comma y. X comma t. X comma t. X comma t.
The row of x comma 0 is f of x.
Row of
X comma 0.
x comma 0. But one more thing, you have to think that A is a fixed constant or anything we have taken randomly or not. That is also you have to check here. Anything relationship is given A for A. There is no relationship is given. There is no relationship. We have taken, I think, randomly. I think that here randomly you can taken that A. Okay. And then rho of x comma 0 equal to f of x. But we have to get in terms of x. Rho of x comma 0 equal to f of x here. This is y plus x comma t form. Therefore, we have to get to y plus ax. Y plus ax. Oh, right. The equation solution is function of y plus ax. Therefore, t comma x you can get here. T comma x. That's why they are taken like that. But the initial condition, if you write y, based on our assumption, you can get y plus function of y plus mx, here. But here t plus ax you can get t plus ax and t minus ax you can get t minus ax you can get. But one mistake we will arrive. I think that you can get t plus ax. Now we have attained some wrong relationship. I think that's why we have to change. I think. Suppose if you put given row to 0, rho of x comma 0 is equal to f of x here, t is equal to 0, and here you can get pi 1 of ax plus pi 2 of minus ax you can get here. Pi 2 of minus ax you can get here. It means that we are getting f of x is equal to pi 1 of ax plus pi 2 of minus ax. That is one equation. Another equation is given as dou rho by dou t. Dou rho by dou t. I think that dou rho by dou t x comma 0. Dou rho by dou t from 1. This is equation 2. From 1. Dou rho by dou t. Dou rho by dou t. What we can get here? That's equal to pi 1 dash of t. Pi 1 dash of t plus ax plus pi 2 dash of t minus ax. T minus ax you can get here. And then t differentiation is 1. t differentiation is 1 only. Therefore, we can get. For this, if you put dou rho by dou t of x comma 0 equal to 0, that is given as 0. 0. Then what you can get here, the left side is 0. You are going to put t0, here is also t0. Pi 1 dash ax, pi 1 dash ax plus pi 2 dash minus ax equal to 0. This is third equation. Third equation. And pi 1 dash ax, pi 2 dash. This is pi 1 ax, pi 2 ax. Pi 2 minus ax. Pi 2 minus ax. Now you differentiate because you have to get this relationship here. If you differentiate, if you integrate this one here, if you integrate this one, pi 1 dash, this is pi 2 dash, pi 2 dash, you can get pi 1 ax plus pi 2 minus ax equal to c, we can get. Integrate equation 3. You can get pi 1 of ax equal to c or k, you can write k, by 1 pi 1 of ax plus pi 2 of minus ax. Pi 2 of minus ax is equal to f of x. So if you are getting these two relationships, but both are same. Both are same. If you integrate here, using 3 and 4, pi 1 is plus you are getting minus pi 2 dash. So after differentiation, you can get here negative value, but we are getting positive. We are getting positive. Because if you are not change x and t, these equations x and t, the reverse manner, this t getting negative. Therefore, dou rho by dou t will get a negative sign here. You can get a negative sign, but we are getting a positive. Both are positive. After derivative also, you can get a positive pi 1 dash and pi 2 dash of t minus ax. If t is negative here, you can get a negative sign here. You cannot get the same equations here, pi 1 dash and pi 2 dash. Here you are getting same sign. Here is also pi and here is also pi. Here is also pi. Okay. You are getting the same sign. For evaluation is both represent same, but here k and here f of x here. F of x here. So we cannot get pi 1 and pi 2 exactly. We cannot get pi 1. So for that purpose, we have to change the equation here. Dou square rho by dou x square equal to LC, you have to change. Instead of a square equal to LC, you have to take a square equal to 1 by LC in order to get that negative value. Yes, it is better to take dou square rho by dou t square first and a square as a 1 by LC. Then you can get proper idea. Yes. If you take dou square rho by dou t square left side here, dou square rho by dou t square left side, this is the equation left side, and you can get 1 by LC. Then in that case you can get this type of equation here. Here this is like a x, this is like a y form. This is like a x, this is like a y form. Then pi 1 of y plus ax, pi 2 of y minus ax, that type of relation you can get here. For the help of these two conditions, you can get these two equations here. But here positive and here negative sign you are getting here. If you integrate this one, you can get pi 1 minus pi 2 equal to c. Now you can solve these two. Pi 1 plus pi 2 f of x equal to c. For pi 1 of x, from this, if you add these two, you can get pi to get cancelled. For 2 pi 1 of x equal to f of x plus c. For pi 1 of x is equal to 1 by 2 f of x plus c by 2. Similarly, pi 2 of x also you can write. Now we are getting pi 1 of x as a 1 by 2 f of x plus c by 2. Therefore, pi 1 can be written as 1 by 2 f of x plus c, and pi 2 also 1 by 2 f of x. Pi 2 also can be written 1 by 2 f of x here. Plus c by 2 minus c by 2 get cancelled here. Therefore, instead of pi 1, you can write 1 by 2 f of x. 1 by 2 f of x plus as again 1 by root LCT, and 1 by 2 f of x minus 1 by root LCT. Yeah. This is rho or v, rho or v. Then you can use the relationship between rho and v and I, current v and I. With the help of that relationship, you can get I here. That is simple. If you find anyone, you can write the relationship between v and I or rho and I. You can write the relationship of another one. Therefore, just fine. So we tried this one as it is here, but if you take as it is here, radio equation as it is here, x in the left side, t in the right side here. If you take a square as a LC, in this situation we are getting a difficulty. Here we are getting a difficulty in order to evaluate pi 1 and pi 2. What is pi 1 and pi 2 based on the initial condition? So in order to avoid this complexity, you have to take reverse manner. You have to take the reverse manner. What is the reverse thing? Dou square rho by dou t square equal to 1 by LC of dou square rho by dou x square. Dou square rho by dou x square. Complexity. Then you write this one as a dou square rho by dou t square. Dou square rho by dou t square. This is a square as a 1 by root here. Sorry, 1 by LC. 1 by LC. A square as a 1 by LC. That is better. Now here you have to take this is t and the x. Everything you have to change. Then here x and t. The remaining things are you have to change. Then you can easily get the relationship. You can easily get. Oh, this relationship you can get x and t, x plus at, x minus at. Here you can get x plus at, x minus at. X plus at, x minus at, this t negative sign you are getting here. Then the problem will be somewhat similar. Otherwise, you are getting a difficulty here in this part here. Or you proceed by this way. This is the correct way. You can get substitute the initial condition. You can get derivative condition also here. If you integrate this derivative, you can get constant. Then solve these two. You can get pi 1 as in terms of 1 by 2 f of x, pi 2 in terms of 1 by 2 f of x minus c by 2. Then you can get the solution. Yes, these two are the two application problem. One is by linear equation. This one by higher order, second order equation. First one is by Lagrange's linear equation. Second one by higher order equation. Okay. These two are the application part. With this, we can conclude the first unit. Tomorrow we'll make some revision here, and day after tomorrow we write the examination. Write the CA1 based on the first unit here. Okay, that's all this session. In the telegraphic equation, we change t and x. T in the first one, x in the right side. Then only you can get easily based on the initial condition. Based on the initial condition, you can get easily the solution. Right, that's all. Okay, that's all this session. If you have any doubt, you can ask me.